Okay, we talked about the production term. Now let's talk about the last term in the turbulent kinetic energy, which is the viscous dissipation of turbulent kinetic energy. So, as you see in here, the viscous dissipation of turbulent kinetic energy is minus 2 times nu times Sij bar. Okay, this Sij is different than capital Sij. Okay, this a small bold type Sij is the fluctuating strain rate. Okay, so 2 times nu times Sij bar, this thing again will always be positive because you have Sij square and number 2 is positive, nu is always positive, so it is always positive. So there is a minus sign in the front, so this whole thing will always be negative in K equation. So this term 3, will always act as a sink and it reduces the turbulent kinetic energy. So we know it as a viscous dissipation of K, which we will see that we show this viscous dissipation of K as epsilon. This dissipation is the same thing. This epsilon is the same thing that uh, we talked about earlier in this section. If you remember, we talked about the energy cascade and the smaller scales get dissipated. And we talked how much energy will they lose in 1 second. You remember this a week before, and we called it energy dissipation rate. And if you remember, we said that it is proportional to U0 cubed over L0. So this is exactly the same epsilon. So that epsilon mathematically appears in our equations in turbulent kinetic equation in here. So if you want to model your turbulence, you need to be able to calculate the value of this epsilon. If you meaning that how much energy do you lose? So mathematically, this epsilon is 2 times nu times Sij bar, and we said that it is always positive. So let me clarify. Okay, at one side you have mean kinetic energy. This mean kinetic energy will be lost in two ways. Either it is directly goes to heat through viscosity, okay, this way, or it is uh, going to turbulence generation. So if it goes to turbulence generation, you will have a turbulent kinetic energy. So turbulent kinetic energy kind of sucks in the energy from this second way, but this turbulent kinetic energy can lose its energy due to only viscosity. Okay, everything goes to heat. Uh, at the end of the day, everything will be dissipated, but mean kinetic energy either dissipates uh, directly to heat or it gives some energy to turbulence and then turbulence gives it to the heat or dissipates it to the heat. So we will talk more about of this later, but this is how we relate all this phenomenological understanding of eddies, energy cascade, and energy loss at smaller scales to the equations. So we have conservation of K, and we have conservation of mean kinetic energy. So we said that we need to know the value of this epsilon, right? This epsilon that comes in turbulent kinetic energy transport equation. Okay, how do we find the value of this? Okay, normally we can do experiments in different turbulent flow fields, and you need to measure the derivative of fluctuations, okay? Because this Sij is nothing but the uh, half of derivative of fluctuations, okay? So you need to first of all measure the instantaneous data, and therefore you also need their spatial distribution, because you need the gradients. Okay, so when you have the spatial distribution, only then you can take the gradients. Actually, before the invention of particle image velocimetry, and I suppose that you have heard about the particle image velocimetry, it was impossible to measure this thing, because you should put a lot of, for example, hot wires all over the place inside the flow. Okay, but today with the use of PIV, you can measure this Sij, but it has to be very, very high resolution, because you are going to deal with gradients. So once you know this, you can multiply it by 2 times nu, and then you can have some estimation of the real number of dissipation level inside your flow field. The thing that we described before to estimate epsilon, so you remember the estimation of dissipation, is something different. So this is directly measuring and directly saying the value of epsilon, but estimation of dissipation is something else. You remember that we said it is in the order of U0 cubed over L0, and that was just an order of magnitude, not the exact value. So it could be, for example, 100, 150, 190, 200, and so on. But the one you get from this equation in here is the actual value, which is obtained either from particle image velocimetry, so you either do experiment or you have to do direct numerical simulation. If you don't have that data on dissipation rate, you cannot model turbulence. For example, in K epsilon model, times, yeah. For example, in K epsilon model, you have K epsilon model. There is a transport equation for epsilon, which is not a theoretical equation. It is very empirical. It is heavily empirical equation, and it tries to estimate the level of dissipation in the flow field. That empirical transport equation has a lot of coefficients, and those coefficients are unknown, and you will try to tune those coefficients if you know what you are going to get at the end of your modeling. So it is kind of silly, because you're going to actually solve something numerically or model turbulence, but first of all, you have to know the solution of that thing. So if you don't know the results, You don't know how to tune those coefficients inside the k epsilon equation, for example, and you can never match the results. So it's very difficult for turbulence modeling to actually model the dissipation physical mechanism and mathematically find out what is its value. On the other hand, LES, or larger dissimulation, does not do this. It does something else. And to know the value of dissipation is one of the reasons that many people do experiments and also do DNS. So it's not, you cannot find the real value of dissipation by LES. Regarding this epsilon, we know that um, actually the physical process of losing energy occurs at smallest scales. So it has to be related to the smallest scales. But you see that we actually estimate it from the larger scales. Now we are going to discuss a little bit back to general description of scales in different types of shear flows and how dissipation is related to all that. And this was actually the starting point of Kolmogorov when he was trying to understand what epsilon is all about. So we are going to continue with the scales in turbulent flows, but let me have a short break for 5 minutes and then I will I'll continue on the topic. Thank you. Okay. In engineering applications, you may encounter with different kinds of turbulent flows, but uh, in reality, turbulent flows can generally be categorized under four different fundamental shear flows, and those shear meaning that we do have a velocity gradient. So the shear flows are either free shear or wall bounded shear. And in free shear flows, you have wakes, jets, and mixing layers. And the wall bounded shears, you have the boundary layers. So what are these? We are talking about, for example, a wake, for example, a cylinder that is exposed to a free stream, and the free stream velocity is u infinity. So you remember that we said if the Reynolds number is high enough, uh, which you pass the laminar, let's say, region, and starts to undergoes the transition, and after the transition, you will have a kind of turbulent flow, turbulent vortices as well. So it will create some turbulent wake behind the cylinder. And if you somehow measure the velocity distribution behind the cylinder, you will see the wake like this. So outside the wake, the velocity is close to free stream velocity, something like u infinity. And within the wake, it reaches to the minimum and more or less in the center of the wake, and then again it increases again. Generally, the wake is characterized by wake width, which you show it by L in here, wake width, and maximum decrease in velocity, or we call it velocity deficit, which is called delta U bar. And as you see at each location of x, each location of x, For example, here in this location of x, the wake has its specific width and has its specific deficit, velocity deficit. And as there is some velocity gradient here, so you see the velocity is changing, so it is a velocity gradient, we have a shear. So the magnitude of this shear is in the order of delta u prime over L. So shear, you know that shear is du dx, right? So in terms of this velocity profile, the velocity u is changing along y direction. So the shear along y direction you have, shear of u bar is in the order of delta u bar over L. So it's in the order of velocity deficit to the wake width. So we are not talking, again, I am insisting that we are not talking about the exact value. We are talking about an estimation. So it is in the order of magnitude comparison. So in here, if it is turbulent, the wake is turbulent wake, the fluctuations are in the order of, again, your delta U bar. So your U prime is the RMS, root mean square of the velocity of the fluctuation. So uh, actually it is U prime is what we had as a fluctuation, uh, RMS of fluctuation. So it's not the fluctuation, it's RMS of the fluctuation. So this U prime is actually indicating the turbulent kinetic energy. You know that turbulent kinetic energy is half of UI prime squared bar. So this is actually the same thing as your RMS. The second type is a jet flow, the second shear flow. What we are talking about is some orifice you can consider, and it issues a turbulent jet outside. And if you take a cross section at one x location, at each x location, and plot the velocity profile, you will get something like this. Outside the jet, actually, the velocity is around zero, and it increases to a maximum value uh, at the center, and then it decreases again to zero. And again, the maximum difference in velocity is called delta U bar, and there is more or less a width of jet that we call it as L again, and these values characterize the general layout of the jet. So uh, your delta U bar is actually the center line velocity. UC means the center, C means center line velocity, which means that it is at y equal to 0. And again, your shear is comparable to the ratio of delta U bar to the L. And again, this U prime is the RMS of uh, fluctuations, which is again in the order of your delta U bar. Next shear flow is the mixing layer. So these are all free shear flows. So what is mixing layer? This is uh, let's say we have a certain plate. This is a plate that is separating two flows. So you have one flow from the top, one flow from the bottom. The top one has a high velocity. The bottom one has low velocity. When the plate ends, after the plate ends, these high and low velocity, high and low momentum, let's say, flows will start to merge. And if you go far away, far away from this plate, this mixing of two different momentum flows will actually create a mixing layer. And in this case, again, there is a certain length associated with this mixing layer. We call it again L. So the length, there is some kind of length, and also there is the velocity difference between the high level and the low level momentum flows at again each x location. So again, you can write the same thing for the mixing layer. And the wall-bounded layers, wall-bounded shear flows like the boundary layers. When we talk about boundary layer flows, we have, let's say, a solid surface, and over this surface, there is a mean velocity profile, as you see. So boundary layer is growing. Uh, and there is a certain length scale associated with the boundary layer. We call it delta, and it is the boundary layer thickness. So in this case, your L is in the order of delta, but you have to note that the definition of velocity scale is different than what we used for free shear flows. Because in free shear flows, we define delta U bar in free shear flows. The delta U bar was the difference between maximum and minimum. And in boundary layer, if you define your delta U bar the same way, it will become U bar because um, for estimation of dissipation, it doesn't work. So you have to use other velocity scale for boundary layer. For example, you define friction velocity U tau, which is based on the surface shear stress. So fluctuations within the boundary layer are more scaled with this velocity than your mean U bar velocity. Boundary layers in itself is a one semester long class, and it requires a specific attention. So we are not going into details of it. And as I put it in here, you can go over Schlichting book. Turbulence scaling in boundary layers will actually fall into a different category, and you can refer to that book as well. Okay, what we will do next is to estimate production and dissipation for all those types of flows, the jets, wakes, mixing layers, and these things. Actually, we want to see that if the production and dissipation will balance each other or not. This is very important. You may ask why. Let's take a look at the transport equation for turbulent kinetic energy again. So this is the conservation of turbulent kinetic energy, K. As you know, redistribution term, you had a redistribution term does not contribute to either generation or dissipation of turbulence. If production and dissipation balance each other in this equation, then except for the fact that turbulent kinetic energy will be redistributed in this space, there will be no generation of turbulent kinetic energy. So if you assume that redistribution is zero and production and dissipation are equal, one is plus, one is minus, so they will cancel out. So there is zero at the right hand side. Okay? So it's very important to understand the balancing between generation and dissipation of turbulence. And we will show um, that those are very much related to the scalings of the turbulence. Let's consider a very simple shear flow. like what I showed to you in here. And it could represent any of those wakes or jets or mixing layers, okay? Those free shear flows that we have defined above. And let's suppose that it's linear distribution. It's linearly changing velocity profile. If you zoom enough to any one of those shear flows, you can see the velocity profile like this actually. So you can make it as a linear variation. For this type of flow, this specific type of flow, dui dxj is du1 dx2. So suppose that this is direction 1, this is direction 2. So your dui dxj is only has one component, what I want to say, and all other components will be 0. So only u1 is changing, and it is changing only along x2. To a first order approximation, assume that turbulence is homogeneous, meaning that whatever spatial gradient we have regarding turbulence in equations will be 0. So gradient of anything in turbulence is equal to 0. Assuming this condition, if you write the transport equation of k again, it will be simplified. It will be simplified to this. So dk dt is equal to 0 plus production minus dissipation. Why the redistribution is 0? Because we said that the divergence, everything related to the divergence in here, and we said that divergence is 0, so the redistribution term will be 0 if it is homogeneous. Okay? Now, for further simplification, suppose that the first order of approximation dk dt is equal to 0. So if it is equal to 0, only the production will be equal to the dissipation. In other words, something generated the turbulent kinetic energy, and it could be wake of a cylinder, it could be jet or something else. But let's assume that if it stays constant in time, then your production will be equal to dissipation. Actually, this is production rate, this is dissipation rate. Okay, rate of production, rate of dissipation. So in the turbulent kinetic energy transport equation, the conservation equation for k, I mean, you remember that you defined the production as this term 2. So here is your production, and once it is equal to the dissipation rate, uh, this will be equal to dissipation. And for simple shear flow, we have shown above indices are reduced to 1 and 2. So just minus, okay, I and j is 1 and 2. Just replace I and j with 1 and 2 in here. And then you have to do an order of magnitude analysis. And if you do an order of magnitude analysis, it means that, okay, these two fluctuations is in the order of u prime squared. The du over dx, as we said, for all of those free shear flows, du bar is in the order of u prime, dx is in the order of some length, right? So you can see that your epsilon is in the order of u prime cubed over L. But there is a problem with this, because if I look at the dissipation term in reality, the dissipation term in reality, meaning this term, there is viscosity 2 times nu, right? Which does not show up in here. There is no viscosity in here. Also, it seems that no matter what you're looking at, no matter what we're looking at, whether it is a jet or wake or mixing layer, some characteristics do not change at high Reynolds number, like the spreading rate of the jet at Reynolds number 10 to the 4 or 10 to the 6. This is also experimentally shown. So some of the scaling parameters stay the same. So it seems that for a strange reason, if you have your delta U bar and your L stay the same for different Reynolds numbers, this epsilon also stays the same. So it's not Reynolds number dependent. Actually, experimental evidence show that if epsilon is independent of Reynolds number, it should also be independent of viscosity. But mathematical equation, again, you see this mathematical equation, this is mathematics, it dictates that it's not independent of viscosity. The viscosity is there. Actually, the viscosity is in the very definition of dissipation. You know this. You know the definition of dissipation. So this actually what we call it is as a dilemma. So it's an argument presenting two or more equally conclusive alternatives against and an opponent. So in the experiments, we observed the independency of epsilon from Reynolds number, but theory says it shouldn't be independent of Reynolds number. So Reynolds number means you know that Reynolds number is rho VL over mu or your VL over nu. So what I mean by Reynolds number is directly related to the nu, which is there inside the epsilon definition. So what's the problem? Actually, Kolmogorov started thinking about this, and then uh, what he explained was if epsilon is independent of Reynolds number, what's going to happen if the Reynolds number is very, very large? For example, infinite Reynolds means uh, when you look at this, if Reynolds number is very, very large, it means that your viscosity goes to zero, right? So if viscosity is close to zero and epsilon is not changing with Reynolds number, meaning that even if viscosity goes towards zero, epsilon always has a finite value and does not change with Reynolds number. So let's look at this. Let's look at this equation. From this equation, it's evident that in this condition something should happen to these two, right? Because epsilon could remain at a finite value. And if you remember, this Sij, as small as ij, was like this. So how can Sij go to very, very, very high values? If you look at this, either the fluctuations should go to higher values, or these gradients or the length scale should go to the very small values. So delta xi and delta xj or dxi dxj should go to 0, and then if they go to 0, Sij will go to infinity. And as nu is decreasing in high Reynolds number, epsilon can stay finite. The next question that we have is that, okay, this has to happen, as we said, in very, very small scales, meaning that these dxi, dxj, or the length scales should go to very, very small values. But how small are these scales? And this is actually what Kolmogorov found out about the scales and the and they call it as a Kolmogorov length scale as well. And we will see it next week, the Kolmogorov length scale and related materials.